Oh, hi. Today we will talk about the power and torque in a synchronous machine. So in the last lecture, we already showed the EF or like induced voltage times the sine delta is equal to XS times IA cos theta. So let me start with a quick review. So let me, I don't know, draw, let's say this is our VT, okay? And let's say you have a lagging power factor, okay, so this is IA vector, so this is our power factor angle. So what I do, okay, I actually add JXS JXS, so it is rotated 90 degrees times IA vector is here, and our EF is the resultant of these two. So that was EF vector, and this was our lambda. So we showed geometrically these two are equal to each other. Let's do it again. So the idea is simple. So I can represent that distance. Okay, so if this is theta, so I can say this is 90 minus theta. So this is 90 minus theta, and that angle, actually this is theta, right? So if this magnitude wise, so I'm talking geometrically, not the phasors or vectors. So the length of that one is XS times IA. Okay, so that distance is equal to XS times IA times cos theta. Okay, and I can write exactly the same thing. So that one is actually, look over here, if this is magnitude wise, if this is EF, okay, magnitude, and that angle is equal to, sorry, that distance is equal to EF times sine delta. So that is, you know, what we showed geometrically. So once we know that one, so we will use that relation in power and torque calculations. So let's write the power equation in terms of EF and other parameters. So what can I, at the end of day, so we have a motor or generator, so we have the machine, so we have phase voltages, okay, let's say we have phase currents and we have phase voltages. So for each phase I have terminal voltage again in the per phase equivalent circuit. This is per phase equivalent phase voltage times voltage times cos theta, is that one is the per phase power, and I'm multiplying by 3. It's a 3-phase machine, and the total power is equal to 3 times VT times IA cos theta. From the previous one, instead of IA cos theta, now I can write EF sine delta divided by XS. Okay, let me write that one. So that one is equal to EF, okay, so sine delta divided by XS, right? So if I put it in place, so that is our synchronous machine power, and that is quite important, and we will use the meaning of that equation in a moment. So again here, this is, let me show, this is all magnitude wise, okay, that is why we don't have J here or the vectors. These are the vectors, RMS magnitudes of those terminal voltage and EF voltage. Okay, so that is the power, right? So again, you can see once there is no load angle, if the rotor and stator MMF are aligned, the load angle will be 0, and in that case we are not generating any force, we are not generating any torque, therefore we are not consuming any power. But again, another important thing, we will see it in the following weeks, but for that equation we neglected the I square array losses in the machine, so it is like 100% efficiency machine. So this is the power. So what can I write about the torque? I know, the machine is rotating with the synchronous speed. So that is the idea of a synchronous generator. So I can write power. Okay, again, I'm ignoring the losses in the rotor or another mechanical losses, which is purely ideal machine, ideal model. So in the ideal model, I know the power is equal to torque times rotational speed. So the important thing, don't make those mistakes. So that is radian per second, first of all, not RPM or not hertz or that kind of things. And secondly, it is the mechanical speed. Okay. So don't forget about that one. Whenever you are putting torque, whenever you are dealing with physical torque, and if you are multiplying it with speed, that is the actual rotational speed, because we know if the number of poles is, let's say, 4, then the electrical frequency will be twice of the mechanical frequency. But whenever you use physical torque, you need to write the mechanical speed. So what I need to do is I need to use, instead of power, I can use that equation. So I can write torque as power divided by omega s, and again, let me write here again, this is the mechanical speed, not electrical speed. So torque will be equal to 3 times Vt times EF magnitudes RMS sine delta divided by XS omega s. Okay, again, at the end of the day, this is not the inductance. You have the J, not J here, but it is the omega L. So there's another omega term in it, but that is with respect to the electrical frequency. Okay, so let's have a look at that equation and its meaning. Okay, so in the very beginning of the synchronous machines, we talk about the torque in in synchronous machines is with respect to the load angle. So the difference between those MMF, if they are perfectly aligned, then there will be no torque, and you generate maximum torque when the derivative is maximum, and that was in a ideal machine, it was 90 degrees. So you have some Tmax. So Tmax now, in the early weeks we talked that one as like as a constant, but we now can write from that equation. Okay, so if this is the load angle, this is changing, we can write the maximum torque like that. So the maximum torque is 3 times Vt times EF divided by XS divided by omega s. Okay, again, as you can see, as the speed is reduced for low speed machines, for the same power rating, you generate more torque. And again, if you somehow manage to reduce the inductance of a machine, equivalent inductance, so you can generate a higher torque. And similarly, increasing voltage and induced voltage is actually another way to increase Tmax. So actually, if you think of that equation, and if you just come back to here, okay, so Tmax here, it is that value, and that value is again minus Tmax, it is ideal. So if, for example, my EF is ahead of the terminal voltage, then it is like pulling the MMF, then it is working as a generator. However, on the other side, if my voltage is ahead of the EF, so it is pulling the rotor, so it is working as a motor, right? So again, that equation is quite important for us. Actually, I would like to emphasize that term. So if you just look at that equation, again, remember, these are all magnitudes, and power can flow in one direction or in the other direction. So this is positive, 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 positive. So the direction of the power flow, let me write here, of power is proportional to sine delta. And if delta is larger than 0, then power flow is larger than 0, because sine, a positive value of sine, again I'm thinking it is between 0 to 90 degrees. Okay, that's the stable point. Or if 9 delta is less than 0, then power flow will be negative. So what does it mean? So that means in an AC machine, okay, in a synchronous machine, let me draw it here. So here you have EF, right? And here you have VT. So here, that is our machine and that is our terminals. Okay, so the power will flow, okay, the power will flow in this way, okay, if VT is ahead of EF, so it is working in the motoring mode, or if it is working as a generator, okay, if it is working as a generator, then the power will flow like that. And whenever it's going to work as a generator, so that means the EF is going to lead, okay, if EF is going to lead VT. And that one is not, I mean, that is the important part, and that is not only for synchronous machines. This is the power, I mean, look at the title. So just this is the generalized power transfer in all AC systems, and AC system doesn't have to be in, you know, just in synchronous machines. If you think about that one, okay, so you can have one AC system on one side and another AC system on the second side. So for example, that can be, I don't know, Kayseri transmission line, and this can be Ankara. So it is like two cities connected to each other with some transmission line. So that transmission line can be represented like an inductance as here. So the question is, if in the transmission line, if the power is flowing from the Kayseri to Ankara or from Ankara to Kayseri, how can you measure that? And actually, you know, you can connect current sensors, voltage sensors, that kind of things. But what you can do, you can connect one oscilloscope here, another oscilloscope there, and you can put these two AC voltages on top of each other, and whichever is the leading, okay, whichever it is the leading, so you can think those two systems as if they are in a synchronous machine, or as if there's a rotor and again donkey and the carrot relation. Whichever it is the leading, it is pulling the other one, right? So it is pulling the other one, so power flows from leading side to lagging side. So that is really important in transmission systems. And actually, when they are doing in the power system, in the stability analysis, that kind of things, you have nodes across all over the, you know, country, so you can represent all that transmission line like a inductance on one side, okay, and at that inductance you can have like VT on one side, V1 on the other side. So basically the power is going to flow from one side to another, or the other way is determined by the leading or lagging relation. And actually it is not only in the, you know, AC systems like a power grid. In the wireless communication, actually that is the same idea. That's an AC system, just the frequencies are higher. For example, if this is your GSM tower, okay, and let's say that is the antenna of your mobile phone, if of course there's like a, you know, bidirectional power flow, but assume GSM is transmitting power to your mobile phone, so it's transmitting information. So actually, if you can capture all those sinusoid waveforms and actually put those things, so if the power is flowing from GSM side to your mobile phone side, so all those high frequency signals, if you put them on an oscilloscope, you will see the, you know, the GSM side will be the leading part, as if it is a rotor of a synchronous machine, or as if it is the again donkey and carrot relation. Okay, and actually it is not also in just electrical systems. We have the same relations in mechanical systems. So that is why I would like to show you this video. So this is a wave energy converter. This is Pelamis. So you can read the full story here. So you know it's quite large, and this put in open sea, and this is generating electricity. So let me show you video. So here you can see it's in operation. Okay, so again it's like a really big snake. It's quite large waves today. The idea is it has some joints, so as the wave moves it's up and down. So you have some hydraulic cylinders, and it's pumping high frequency, I don't know, I think fluids, and then it is accumulated in a tank. Then it's rotating some electrical machine, and it is connected to shore with some electrical cable, so you can generate some electricity from the waves. But I don't want you to emphasize the electrical system, but look at the mechanical system, because you have now sea waves going up and down. So that is our V1, and then we have the big snake, you know, that Pelamis device that is going up and down. So that's another AC movement, sinusoidal movement. So that is our V2, and the inductance now is the inertia. Okay, so the power transfer from waves to machine itself will be determined by the phase difference between these two AC systems, right? Look at how it moves. So it's connected to seabed with some anchor. Let me show that part. So now look at the phase difference between the movement of the snake and the waves. First, the waves are coming, so the snake, Pelamis device is submerged under the water. Then there's a phase difference, then it goes up, then the wave has already passed, so it will go quite a lot out of the water. So the phase difference between the actual movement and the waves determines the mechanical power flow between these two devices. Okay, so now the waves coming, so it's submerged, the waves are going out. Now it's its maximum. Here actually it can move in, you know, two directions, upside down and sideways. But look at the coming of the waves. And actually if the device is moving actually at the same time with the waves, there will be no force. In other words, there will be no load angle, and if there's no load angle, there will be no force. If you know, you cannot generate any power. In order to generate some power from the waves, the actual movement of the device has to have some phase difference with respect to waves. So that's why, you know, you need to be really understanding that one. I mean, in the previous years and circuit you used with the DC systems, and in DC systems you can say power flows from high potential to low potential, right? So you can have, I don't know, an inductance, so you can have V2 and V1, right? So if V1 is larger than V2, then the power will flow in that direction, or if it is smaller, it is vice versa. So you can quickly calculate the phase difference, you know, divide by resistance or any impedance in between, and then you can calculate the power. But that is not the case in AC systems. Okay, the magnitude has no importance at all. So in AC systems, power flows from leading voltage source to lagging voltage source. Okay, the sign of the load angle determines the direction of the power flow, and it doesn't have to do like really with the electromechanical energy conversion or that kind of things. That is the same in wireless power. or that's the same in like wave energy devices. Whenever you have some sinusoids, okay, so let me again show you the same analogy here. So you have V2, V1, okay, this is AC, this is AC at the same frequency. That is important. The power direction, okay, if you cannot say like V1 magnitude is smaller than V2 magnitude, so the power flows from that side to here, okay, that doesn't have to be any importance. Even if it is like 100 volts RMS and this can be like 1000 volts RMS, I mean, even in that condition, if V1 is leading, okay, if you put those two vectors, if like V1 is like that, V2 is like that, it can be like larger in magnitude. But if V1 is leading V2, then the power will flow in that direction. Okay, so that is really important, and it has like many applications in different area of electrical and mechanical engineering. Okay, thank you.